Hello everyone, in this video we are just going to interface push buttons with Renesas RL78 bar F14 series microcontroller R5F10 PPJ. Let's get started. So before going to the programming part, let me just show you the development board user manual for understanding if there is any push button available in it. So this is the user manual of the development board or target board that I am using in this course, that is QBR510PPJ. So in this development board we already found that there are two LEDs, that is two onboard LEDs available. One is LED 1 which is connected to P66 pin of the microcontroller, and LED 2 which is connected to P67 pin of the microcontroller. And we have another SW1 push button which is connected to INT P0. So we can use this push button for interfacing this particular push button with our microcontroller. So what is the exact pin number of INT P0? So this INT P0 is nothing but interrupt pin of the microcontroller, that is external interrupt pin. So let me just exactly find out the port pin number. So when I go to the schematic in the next page of this user manual, you can see this is the SW1 push button which is connected to P137, that is port 13 7th pin, and this has been configured in pull-up logic. So in the last video we just learned two different logics for interfacing push buttons with our microcontroller. One is the pull-up and pull-down. So in this particular pull-up logic we'll be having high signal in the port pin whenever the button is in released state, and whenever the button is pressed we'll be having the low signal. So low in this particular P137 pin represents that the switch is pressed, and high in this particular pin P137 represents that the push button is in released state. So the pull-up logic push button SW1 is connected to P137 of the development board, and also we will be configuring the same LED, that is this LED 1 which is connected to P66 as output device, and we will be utilizing this also in our program. So now let us try to open the CubeSuite Plus for CCRL IDE for creating our project for the microcontroller. You can see in this IDE opened, I'm just going to create my new project. Just click on the project tab in the top of the window and then hover over this create new project and click on it for creating your new project. And in the window that is popping out, just type in the microcontroller name. In my case I'm just typing R5F10 PPJ, and you can see the highlighted microcontroller will be selected by default. So just cross verify that the pin number is correct for your microcontroller. In my case it is 100 pin, it is correct, so I'm just leaving it. Or if it is anything different like this one or this one, just click on select anything as per your requirement. Just left click and select it as per your requirement. And once after selecting the microcontroller, just provide a name for your project in this project name tab. I'm just providing it to be Pro. And in place of this place tab, just click on this browse button for selecting the repository or directory in your local folders where you want the project to be stored. So let me just make a folder right over here, RL78, and I'm selecting that folder, and I'm clicking on the create button for creating my project for this particular microcontroller selected. You can see on the left of the IDE we are having a particular tab called project tree. So this particular tab will be containing several segments of the microcontroller. Those are very important. First and foremost segment is the pin configurator segment, and next segment is the code generator segment, and the next segment is the file segment. So these three are the major segments that is generated for your microcontroller. So this pin configurator segment is useful for visualizing the configurations that has been done for your particular microcontroller. So when I double click on this device top view, you can clearly see this is the layout diagram of my microcontroller RL78 bar F14, that is R5F10PPJ. You can see each pin description has been provided right over here. Once the configurations is done, you can see the configurations that has been done as a whole in this layout. So for that purpose, this pin configurator has been provided. So using this code generator segment right over here, you will be able to generate your own base peripheral software that is required for your microcontroller as per your user application. So I will be showing you how to configure your microcontroller in a while as per your application needs. But before that, we just want to do some basic configurations that needs to be done for almost all the programs. Just double click on this clock generator tab inside the code generator, and you can see these configurations, that is the default configurations that needs to be fixed in the microcontroller before moving on. So let's take an example. This particular PIOR00 is yet to be assigned to the function TI00, and the respective port pin for that function is P17 by default. So if you need any alternate port pin to be configured for this function, let's check it out. Just click on this drop down. You can see the alternate pin that can be assigned with the same function is P66. So if you want that particular pin to have this feature, you just want to select that. So most often we will not be changing anything right over here. We can use all these functions for all these pins as it is. So if in case anything is required, I will just intimate you in future lecture videos. But for now, we will be fixing these settings by default. Just click on fix settings for fixing these settings as default settings in this microcontroller. Once that is done, just click on chip debug settings tab right over here. And this is a tab which is useful for enabling the debug option in your microcontroller. So if this is disabled, you will not be able to program your microcontroller using debugger, or you will not be able to debug your microcontroller using debuggers like E1, E2, E2 Lite, etc. So for that, just click on used radio button right over here. In my case, I'm just going to select the E1 right over here. If you are using any other emulators like E2 or E2 Lite, you just want to select the respective radio buttons right over here. So in my case, I'm just leaving this to be E1 selected. That's all about the basic configurations that you want to do. In addition to that, just double click on this watchdog timer right over here in the project tree inside the code generator, and you can see by default this watchdog timer is enabled, or it is used by the code generator. So you just want to disable it. So I will teach you what is this watchdog and how to configure this watchdog in this microcontroller in a separate video. And for now, for almost all the videos, I will be disabling this watchdog, and in a separate video we will learn how to enable the watchdog and how to utilize its features for safeguarding our microcontroller. That's it. These are all the required basic configurations that you want to do for almost all the programs. So now let's just move for configuring our microcontroller as per our application needs. So as we discussed, we need P66 pin to be configured as output for using the LED 1, and P137 pin to be configured as input for using the push button that is available in the development board that we are working on. So these are the two configurations that needs to be done. P66 port pin must be configured as output for LED 1 for using the LED 1 available in the development board, and P137 pin must be configured as input pin for using the push button that is available in the development board. So just double click on this port, going to the port 6, just click on this port 6 tab, and for configuring this particular P66 pin to be output, just click on this radio button out. You can see the configuration is done and the P66 pin has been configured as output. And again, coming to the port 13 right over here, just click on the tab port 13, and then here I just want the P13 pin to be configured as input. So in this particular pin, you can clearly see you cannot configure this particular pin as output. So the only option that you can do is you just want to configure it as input or unused. That's it. And we are done with the configuration. We have configured the port 13.7 pin as input and port 6.6 pin as output. Now click on this generate code for generating your code. That is the base software required for these configurations, that is the digital peripheral configurations. You can see once after I have clicked this generate code button right over here, there is one folder that has been created inside the file folder. That is the code generator folder. Just click on the plus near to it. You can see these are the base software generator for us. That is the peripheral base software as per our configurations that has been generated. So opening the rmain.c, which is the main source file. You can see this is the main function, and one more function we have. One is the main user init function. So there are two parts of program that is available in an embedded program, as we discussed before. One is the initialization segment, another one is the infinite segment. So in initialization segment, we will be writing down the programming lines that needs to be executed only once in the lifetime of the program, and but in the infinite sequence, that is in this while of 1, we will be writing down some programming lines which needs to be executed again and again until the microcontroller is stopped. So this is the logical part of the program which needs to be executed again and again until the microcontroller is stopped. But the programming lines just before the while of 1 or infinite loop is called initialization segment, which needs to be executed only once in the lifetime of the program, in the beginning stage of the program. So for this particular initialization segment, we are having user init function. You can see right over here. So whatever the initial code that you want to write, you can just write it right over here inside this function, and whatever the logical part that you want to write, you can write inside this while of 1. So in the last one of our video, we just learned some technique for reading the status of register bits in a microcontroller. So in the logical part, what we are going to do is we are just going to perform an application or build an application when SW1 is pressed. I want the LED 1 turned on. When SW1 is in released state, I want the LED 1 to be turned off. That's it. So whenever I press and hold this SW1, I just want the LED 1 to be turned on, and whenever I just want the SW1 to be in released state, I just want the LED to be in off state. That's it. So in previous one of our video, we just learned some important technique for reading status of a particular bit in a register of a microcontroller using some bitwise and logical operators, right? So we are just going to use the same technique right over here for reading the status of port register in this microcontroller. So let me just take out the sequence that we discussed in that video. So the sequence goes like this, that is variable is equal to register ampersand of 1 left shifted by bit number, and as a whole bit number, right shifted by bit number times. So this is the sequence which we discussed in last one of our video for reading a register bits status of the microcontroller, for reading any register bit status of microcontroller. So we are just going to do the same right over here for the port 13 for bit number 7. So we know the SW1 is connected to P13.7 and LED1 is connected to P6.6. So we are just going to read the P13 register bit number 7. So let me just use a variable called button state, and P13 ampersand of 1 left shifted by 7 times, right shifted by 7 times. If button state is equal to 0, I will turn on LED1. So we already learned some methodologies for turning on an LED. So I just want to clear that particular bit for turning on the LED. So we very well know the onboard push button that is available in this development board is configured in pull-up logic. So whenever the push button is in pressed state, whenever I press this push button, I will get a low signal right over here, and whenever I release this push button, I will get a high signal in this particular GPIO pin P13.7. So here pressed means low signal in the GPIO pin, and released means high signal in that particular GPIO port pin. So whenever I get a low signal or the button pressed, I will turn on the LED by making that particular port pin to be low. So as we know, LED1, which is connected to P66 right over here, will be turned on only when this P66 pin is low, as this is connected to cathode of the LED. And whenever I make this pin high, I will get this LED turned off. So as per the hardware configurations available, we are just writing down our program. So if you are using any other different development board, please make sure that your program that you are writing is in sequence or in sync with the hardware configurations done. If the particular GPIO pin is connected to anode of the LED, you just want to make the particular pin to be high for turning on the LED. In my case, it is connected to cathode, that's why I am just making the GPIO pin to be low for turning on the LED, and here I just want to make the GPIO pin high for turning off the LED. I'm just going to declare this button state variable right over here, and this global variables and function declaration segment, just in between the start user code and end user code comments. I'm just going to declare this and initialize it to 0. I just left one bracket right over here. That's it. Now you can see inside the infinite loop, I'm just reading the status of the bit number 7 in P13 register. If it is 0, I'm just turning on the LED. If it is not, I'm just turning off the LED. So whenever the button is pressed, I will be having the value 0 right over here as the result of this expression, and I will be turning on the LED if the value is 0, and if it is not, I will be just turning on the LED. So since all these lines are written inside the while of 1 right over here, these lines will be continuously being executed in the logical segment of the program until the microcontroller is stopped. And I have already connected my E1 emulator to the PC through mini USB cable, and also the FRC 14 pin connector has been already connected to development board connector. So let's check out the hardware connections and come back. So I hope you understood what is the hardware connections made. I just powered up my development board with the help of 5 volt 3 amps SMPS, and I have connected my E1 serial debugger to my development board, and the E1 serial debugger has been already connected to my PC USB port through mini USB cable. Now for selecting the particular emulator device, just right click on this debug tool in this project tree, and then hover over using debug tool, and then select RL78 E1 serial, which is the debug tool that I am using. So if in case you are using any other debug tool like E2, E2 Lite, etc., you can just select the respective debug tool. So high recommendation that I am preferring for this E1 serial is E2 Lite, which is most cost affordable. But if in case if you are having anything like E2 or any other E20 like this, you can just select it, no problem. And then click on this button for building this project, or you can also click on F7 in your keyboard for building your project. You can see I'm getting 0 errors and 0 warnings. Now when I click on this icon right over here or F6 in my keyboard, the program will be dumped to my microcontroller. You can see the programming is being done or dumped to my microcontroller. And now click on this play button right over here for executing your program. So now you can see on the development board, this is the user push button. This is the user push button, and this one is the LD2 or the LED2, which is connected to P67, and this push button is connected to P137 of the microcontroller. So as per our logic, whenever I press and hold this button, you can see the LED is turned on, and whenever I release the button, the LED is turned off. So the program is working as expected. So this is the output that I got in my hardware. So I'm just clicking on the stop button for stopping my program execution in my microcontroller. Since we have connected the debugger to the microcontroller right over here, you just want to control the program running and stopping sequence in this IDE. If you want the program to be executed in a standalone manner in your microcontroller, you just want to remove the debugger and reset the microcontroller so that the program will run independent of the debugger in the development board. So I'm just clicking on this disconnect from debug tool for moving my IDE to the editor view.